So nice to see Mark's face again. It's been a while.
It has.
So Mark did his PhD work at San Diego State. I mean, you probably just figured that out. In the computational science program. And he finished that in 2015. He was working in my group on the structure and rheology of self-associating polymer networks. And then he went to a postdoc in Sandia. I think he immediately made more than we do here as professors. I'm not going to ask him what he makes now. So, but that was, he really wanted to go to the national labs. He had like 3 or 4 interviews, pretty successful. And he was also very successful there because he became, a year ago or so, a senior member of the technical staff. And he's been moving from polymers to more silicate. But today's talk, as you can see the title, which I don't have in front of me, so Mark will put that up. I'm sorry about that. So his talk will be also about glasses, which is of course something that I teach in my polymers class, and that I think Mark has been first introduced to in that class when he took it from me. And so here is the title: Silica-Based Glasses, Realizing Process Structure Property Connections Through Computational Modeling. Thank you. Take it from here.
Thank you, Arlette. Are we good there? Should I minimize this thing? Okay, I'd like to thank Arlette for the introduction. Thank you, Jose Castillo, for inviting me to share some of this work. And thank you everybody for showing up, specifically due to the fact that, you know, we are in questionable times with our current health situation. So thank you. I hope everybody is well. So as Arlette had mentioned, I've been at Sandia Labs since I graduated. And I've been working, since I've been there, I've had the opportunity to work in a multitude of material systems, ranging from polymeric materials all the way up to silica-based glasses, to metals, to additive manufacturing. And often, because I'm a computational modeler and I particularly do molecular dynamics, I operate at the atomistic length scale, I'm usually approached with a question that ranges from something along the lines of, hey, we observed this property or this failure mode of a given material. Can you tell us exactly what's going on here? Can you give us insight into the mechanism that gives rise to this type of say, failure or behavior? And so ultimately what that really boils down to is me trying to make connections between what sort of process created the material, what sort of microstructure might exist because of that processing, and what sort of property results from this. Ultimately, this process structure property connection leads to performance of a material. And that's a very, it's a fundamental aspect of material science that this process structure property performance relationship exists. And what we really try to do in terms of materials modeling is try and start to make those connections. And so I wanted to try and demonstrate that in terms of silica-based glasses, where I've been spending a little bit of my time most recently. So the glass age, it has been said that we are currently in a glass age. Now that might be similar to, say, the Iron Age or the Bronze Age, where a given material pretty much kind of is embedded in the technology that you have. And so I wanted to give some examples of where glass fits into our current technology and where we've learned and when we've learned about materials. So I have quite a few examples here up on the upper left. Construction materials, we've long since used glass in construction materials. However, today you could go to some downtown and you would find the entire facade of a given building covered in glass. And that's a big statement about the fact that we understand how glass behaves and we know how it would fail, primarily due to the fact that if a glass pane failed here, it could be extremely dangerous. And that might be a naive assumption to state that we know exactly how that glass is going to fail. Moving on, when we go to electrical components, silicon wafers have really changed the way that we have used electronics. We can produce these substrates with near nanoscale precision, near atomic scale precision, and that really allows us to start making electronic components smaller and smaller. Without that capability, we would be limited in the decreasing size of our electronics. Moving on, optical fibers. Optical fibers are now data transmission lines, right? So the backbone of the internet is probably an optical fiber. I know that there's several companies out there that are stating, what is it, fiber optics to the door, right? So that's the ultimate goal, is the fact that we can send data along these transmission lines relatively quickly. I note that optical fibers happen to be pristine silicates possible, in the fact that they ultimately can exhibit strengths that are very close to theoretical strengths, and they still remain a very flexible material. So that's quite an interesting property for the material. Moving down, there are cell phone displays, right? So Apple been using, well, Apple specifically has implemented what's referred to as Gorilla Glass. That was back in 2006 where Gorilla Glass was introduced, and ultimately it increased the strength of glass in general. Apple has become so confident in this that they have actually started making the entire form factor of your phone in glass. And even though they have this confidence, we all still have probably been exposed to breaking a cell phone screen, right? Even though we have this great confidence, we can't mitigate the failure mode that is, say, impact. Now, a lot of us might consider a broken cell phone screen to be kind of a high consequence application, but in the fact that you have to go spend another $150 probably to go and fix your screen, or maybe a new phone is in the market at that point. But I really wanted to point out a high consequence application, and that being, say, the windows of a space vehicle. I don't know necessarily that NASA is currently using silica-based glasses, but that's where it started. Having a failure of one of those glasses is significantly high consequence in the fact that lives might be lost, right? And so the general idea here and the overall arching thing behind this is the fact that these large institutions, NASA, Apple, Corning, Intel, these large companies still to this day are very much interested in understanding the behavior of glass, how it fractures, what we can do to modify it to try and understand its overall performance and behavior. So in terms of those process structure property relationships, I wanted to highlight just a couple of them. For instance, one of them is tempering glass. We're all very familiar with a tempered glass. It is consistent with your windshield to some degree, given your windshield's a laminate, but the tempering process is intended to give a very final result during fracture. You intend on having very small pieces being produced within what remains of a fractured glass. That's a lot safer than having large shards that would be consistent with an annealed glass. Another example is what's referred to as a Prince Rupert drop. If you're not familiar with this, I highly recommend you go onto YouTube and search this. There are many videos out there describing its mechanical performance, and just in general, let me try and describe exactly how it's made. You would take molten glass and you would pour it into a container containing water. The result is that the exterior of the molten bulb here actually solidifies first, that puts the exterior surface in compression while the interior will be in tension. And as a result, it can withstand some significantly high compressive forces. So a lot of these videos show people hitting the bulb with a hammer and it doesn't fracture. It's quite impressive. The one way that you can break this Rupert drop is to break the tail of it. It breaks relatively easily, but the result is that the entirety will fracture to near powder size remnants. So it's quite an impressive thing, the fact that changing the way that we process this given material, we can ultimately affect the failure behavior of it. Now, one final example, I wanted to talk about glass ceramics. Glass ceramics are, it's a mixture of phases. It's a mixture of a crystalline phase and a more amorphous type phase. However, well, so in what I'm showing here, the light matrix is the glass phase, where the darker region is the more crystalline type phase. However, to get that crystalline phase to form, you have to have a very specific temperature profile in order to produce it. You initially flow something that is basically glassy, and then you hold it there and maybe potentially slowly cool it. But depending upon that temperature profile, you will change the microstructure that is within a glass ceramic. And so this is once again another condition where processing conditions vary microstructure, and microstructure or processing conditions give rise to variations in performance of a given material. And then if we start to talk about at the atomistic scale, what exactly is going on in terms of these process structure relationships, it's important to note that when people typically think about a glass, they think of something that's completely amorphous, lacking structure, and that's not necessarily the case. Silica-based glasses, which are primarily about 60 to 70% silicon and oxygen, typically have short and medium range order. And so the short range order are these silica oxygen tetrahedras that are shown up on the top left here. The medium range order would be a collection of these tetrahedra that ultimately form, say, a ring. So what silica-based glass is lacking is a long-range structural order. And that's something consistent with, say, what you would think of a crystalline metal having long-range order. So anyways, my point being is that using atomistic molecular dynamics, people have started to look at, say, ring size distributions and the influence of thermal cooling rates and how that distribution changes with cooling. That's the lower right-hand figure. The upper right-hand figure is the angle of a silicon-oxygen-silicon bond. And they're showing that, once again, with various cooling rates of the material, they ultimately show differences in that probability distribution of angles that you would see within the material. So this type of process structure property relationship is seen throughout length scales. And it's one of those important things to try and understand how a material performs ultimately. So why is Sandia interested in this? Well, I'm showing a cross-section of one component that is of significant importance for Sandia. And this is often referred to as a glass to metal seal. It's a cross-section of an electrical connector, right? So ultimately the outside of the connector is made of stainless steel. There are electrically conductive metal pins that go through this insulating glass, right? Now the glass, which is highlighted in blue there, the glass actually acts as, has two intentions right there. First off, it serves as an electrical standoff between the electrical pins. And the second is it's actually a hermetic seal. One of the things that they're interested in is making sure that the environment at the head of the electrical connector does not actually interact with the environment at the tail of the electrical connector. And so as such, one of the design requirements for this glass to metal seal is that they have to have that glass in compression. And so with very specific coefficients of thermal expansion of the glass relative to the pin and relative to the metal housing, they can assure that the glass will be in a compression state, enforcing this type of seal, this hermetic seal. And not surprisingly, these seals fail. And I wanted to share a few of the ways that they do fail. These are the lower figures. On the lower left-hand side, we're actually looking at one of the connectors head-on into the pins there. The bronze colors are the pins that are sticking through the glass, which is the blue material in between each one of the pins. The quantity of pins is not important. You could have a single pin or a multi-pin connector, but the inset really shows exactly what's taking place here. You give the glass undergoes some very unique stress states. And as a consequence, often what happens is you might have a radial crack originating from one of these pins, or you might have a delamination between the housing and the glass itself. And immediately, as soon as somebody sees one of these fractures, the first question on their mind is it hermetic? And can we make predictions about this? And how long will it last if we continue to use it? And that's a difficult question to answer. So typically when they see these types of failures, they ultimately will just fail the component itself and then move on to the next one. So another method for a failure mode for this type of seal is shown in the center here, right? This is kind of a half moon chip out that is localized about the pin, and how this might have occurred is maybe a deflection in the pin, which ultimately gives rise to a failure within the glassy material. But once again, this would be a failure situation. And as I had brought up before, often they use glass ceramics and not just glasses. And they sometimes choose glass ceramics because they are stronger. However, they also give rise to more complex type of failure. For example, I want to highlight here on the upper right-hand, you see a fracture that is along the interface of a crystalline region and that of a glassy matrix. And so the complexity of how a fracture either decides to propagate along this interface or traverse through a crystalline region is not an easy question to answer. And these are the types of things that Sandia is interested in. Most specifically, they're trying to make reliability predictions on the order of decades. And that's an extremely difficult thing, especially when we can't predict how fracture occurs under very specific loads. But when you start thinking about 30 years and the fact that these components will be out in the environment, you need to start thinking about possible chemistries that might arise. For example, mechanical loading is not the only contributor that would happen, contributor to failure. More specifically, water actually acts as a corrosive agent. With the addition of water, you will actually find subcritical crack growth. And what I mean by subcritical crack growth is the fact that at stresses below the strength of the material, you will actually have cracks propagate. Now, today I'm going to be talking a lot about fracture toughness, and fracture toughness has a very specific meaning. It is the stress state of a given material that is necessary to propagate a crack. And so these subcritical crack growths are associated with stress states that are below the fracture toughness. So about 50 years ago, one of the seminal works describing this type of behavior actually showed as a function of relative humidity, increasing relative humidity, the crack velocity increases. But I must note that all of these data points here are at stress states that are subcritical. And so this really highlights the fact that it's not necessarily mechanical loading that forces cracks to take place. What's referred to as subcritical or slow crack growth can occur as a chemistry or as a chemical interaction. What we've later started to understand is the fact that the presence of water can actually drop the energetic barrier of a silicon oxygen bond by a factor of 5. And so that's quite significant in the case where, you know, long duration glasses surviving long duration environmental conditions is what you're shooting for. I must note that it's not just soda-lime glass that exhibits this property. There are a multitude of silicate glasses with different contributions from different ions that ultimately exhibit this slow crack growth or subcritical type crack growth occurring. Okay, so materials modeling. So in general, the previous slides kind of describe why we're interested in fracture and why we're interested in glasses. More specifically, I am interested in utilizing atomistic modeling, specifically for the role that chemistry, that we can model chemistry specifically. Atomistic modeling allows us chemical specificity. It allows us to model microstructural content. These are two features that are typically unavailable to other length scale modeling efforts, or more challenging for other length scale modeling efforts to incorporate. And so what I'm showing here is a plot of the modeling time scale as a function of the modeling length scale. And I stole a few figures from a few of my colleagues at Sandia that have done quite a bit of work in other length scale modeling efforts. And so I just kind of wanted to show, you know, at the pico length scale down here at the very finest, this would be density functional theory, where we might be interested in the electronic contributions to materials modeling. Whereas at the upper length scales here, at the part scale, where we're looking at, say, centimeters or meters in length scale, they're typically interested in, say, residual stress or how the part actually performs or fails in general. And so the biggest thing that I want to highlight here is the material representation across these length scales. In the higher length scale up here, we have a continuum representation of material, right? So you have material properties that are associated with given volumes of the material, but in essence, it's basically a continuous space. Down in the lower length scales, we have a discrete material representation where we're actually modeling each individual atom or each individual electron cloud, basically, at that point, I guess. But there's definitely a difference between those two material representations. And specifically, one of the key features is that we often observe and quantify material performance in this continuum representation, whereas what's often the case is that this behavior of these material representations have their origins down in these lower length scales. Now the challenge, especially me operating in the atomistic regime, is the fact that what I want to do is maintain this chemical specificity and microstructural content and assess what role it plays in a continuum measure. And so it's necessary for us to make that length scale jump between what we observe down here at the lowest length scale and the measure that would be applicable to a more higher length scale representation. And so that's my intention today. I want to talk about fracture and glasses. I want to talk about how I'm trying to make that connection Specifically, I'm going to focus on fracture toughness of a material. And once again, that's a stress state of a given material, and I'll be talking about that a lot more. So benefits of atomistic modeling, I've already mentioned, chemical specificity and microstructural content. The challenges, we all have challenges at different length scale modeling efforts, but however, I must note at the atomistic length scale, our typical modeling samples are only on the order of nanometers, and we operate in the time range of nanoseconds. And so it's a difficult thing to convince somebody that when you're operating at these extremely low length scales and extremely short time scales, how can you say that that is a good material representation when you're trying to model the behavior of the part scale? So that's the ultimate goal, is to be able to make that connection between these low length scales and the continuum.
Hey,
okay,
Mark, this is Sachi. Can I interrupt you for a second?
Sure, yeah.
Yeah, there are a couple of questions on the chat from the audience. One was, is that loading on that graph cyclic or monotonic? The one, I think that must be previous graph, I suppose. It's
Here on the left?
on the previous slide, I think.
The previous.
Yeah.
Here?
The crack velocity versus applied force, I'm assuming. Yeah.
Oh, here. It's not cyclic. It's a double cantilever experiment. So what they do is they take a sample which is cracked in the has a pre-notch crack in the vertical direction, and what they would, let's see if I can do. I don't know if I can align my hands correctly. They pull it. They give it a constant moment. And so the force that's being applied on it is just holding it open or putting a constant force on it. And so you allow that to sit there for a duration of time in environmental conditions, and ultimately they will take images and track the velocity of the crack.
Okay. There's another question that says, on the crack velocity graph, does temperature also contribute to crack velocity, or is it just because there is relative humidity?
Most definitely. Temperature will definitely affect that. And if we think about this in terms of atomistic modeling, I'm going to relate it back to it. There's an energetic barrier necessary to break a silicon-oxygen bond, and temperature plays a significant role in that. So if we break fracture down to the simplest form of bond-breaking type of events, then temperature will explore that energetic barrier more significantly than lower temperatures. Yeah.
Okay, thank you.
Yeah, sure. Okay, so just real briefly, molecular dynamics. I don't know if this is really appropriate, but just to just let you know exactly what I'm doing here. In essence, molecular dynamics at its simplest state is integrating the equations of motion on a per atom basis, right? So you have here a demonstration of that. You have the mass, acceleration, plus some function that may be a function of velocity or position. And ultimately, you're relating that to the energetic interaction between each individual pairwise contribution across a given neighborhood, right? So molecular dynamics ultimately breaks down to defining this energetic contribution. Now, that energetic contribution is typically referred to as the interatomic potential. So one very famous one is the Leonard-Jones potential, and it's been around since 1924. And I'll tell you what, still to this day, I use that potential. So it's shown its utility, and it's still very valuable in computational material science, specifically in atomistics. So don't discredit it, even though it's very old. But more recently, what has become very popular are reactive force fields, more specifically REACS-FF. And I note that it's a very complicated energetic term that consists of a multitude of different energetic contributions, but its ultimate goal, it makes an assumption that the bond order between elemental constituents can actually be distance dependent. And it makes estimates to bond order on continuous scales relative to interatomic distance. And so with the knowledge of a given bond order and with the capability to start looking at partial charges that are adjusted given a configurational state, we can start now modeling more accurately chemistry, more specifically chemistry. So we have a reversible bonding type of approach that can ultimately adjust energetic charges, and finally, it's ultimately one of the more advanced methodologies for atomistic molecular dynamics at this point in time. And so I use that interatomic potential to make an atomic glass, and ultimately I'm going to make a fracture sample, and then we're going to quantify its performance. So just a little highlight of where we're headed here. So how do you make an atomic glass? Well, you start off with a crystalline form of, say, alpha quartz. It's a crystalline form, and we will bring it to temperature. You bring it up to a very high temperature, and what will happen is the glass, or the quartz will melt. It will form a liquid, and you hold it there for a duration of time and ultimately start to cool down that liquid. It will at that point solidify, and we will start forming those tetrahedra that I was talking about earlier, and those ring structures. And as you can see, there's many silicon-oxygen repeats within this material, and that's exactly what we're looking for to start with. I note that even after this initial cooling, the system might be in a very unfavorable state energetically and in its density, and as such we bring the system back up to above melting temperature, and then a little bit later on I'm going to be showing results where I explore differing cooling rates and the properties that arise from those. So that's kind of the general thermal history that gives rise to one of these silica slabs. People in the past have done quite a bit of work of quantifying the structure relative to experiment, and you can do so almost nearly directly using neutron diffraction or using X-ray diffraction data. With that data, you can actually almost directly compare it to molecular dynamics. I note that if I push, pull, stretch, etc., this silica sample, I can back out, say, the elastic tensor. So I know that its density is relatively close to experimental at this point, and its elastic properties are somewhat consistent with what I would find experimentally. I note that the shear modulus is slightly lower than experiment, and the Poisson ratio is slightly higher than experiment. That's not too uncommon, and I note that using this atomic potential, it does significantly better than many of the other silica-based interatomic potentials. So I think we're doing quite well in terms of comparison to experiment at this point. So now that we have a glass sample, the next step is to build a fracture sample. And I do so by applying a stress on the material. So I'm going to pull the sample in uniaxial tension in the horizontal direction, and I'm going to deform the material finely and hold it in constant tension. At that point, I initiate a crack up here in the top of the sample just by punching out a few atoms along a given region. And at that point, we can start to run dynamics. And by running dynamics through molecular dynamics approaches, the relaxation state or the relaxation process will ultimately propagate a crack throughout this sample, and this crack will ultimately go entirely through the sample given sufficient amount of simulation time. Now, what's important and what we want to get at here is going back to this idea of trying to understand fracture toughness. I am going to be calculating the stress intensity factors of this atomistic simulation on a per time step basis. And so that's the methodology that I'm going to be talking about today. We have a kind of novel approach to to determine the stress intensity factors. But I want to note that although it was designed for atomistic modeling, our approach can be applied to any full field displacement solution. So some examples where it might be applicable could be digital image correlation. This is a methodology that's used to look at, say, the failure of metals. Also, finite element approaches of fracture. That's a computational method where there's not so much noise within the displacement field. So ultimately, our approach will be to model the displacement field in an annulus surrounding a given crack tip. And I'll describe that a little bit further here. But once again, the question I'm trying to get at is, what role does chemistry and processing conditions have on fracture toughness? So note, fracture toughness is a continuum scale measure, so I'm making that connection between length scales by doing so as well. So since we're going to be modeling displacement fields, it's important to note that atomistic displacement fields are extremely noisy. You often find fluctuations on the order of angstroms. And so I'm just kind of highlighting that there is a distribution of displacements that range from one time step to the next. And that noise originates from temperature within the system. So more temperature, the variance in that distribution increases. And given the fact that we're modeling displacements that contain this noise, I think it's important to quantify the error in the method associated with that noise. And so I'm gonna describe a little bit about how we try to quantify that error. So modeling displacement fields. These are, I'm gonna be using the Williams expansion in order to model this displacement field. These are linear elastic fracture mechanics fields. Linear elastic fracture mechanics originates from continuum assumptions about materials. But ultimately, these displacement fields describe the Cartesian displacements U and V relative to your sample in X and Y. So you have a crack tip centered at the origin here, and you have crack faces that propagate off into the negative X direction here. So the X axis is along the central crack face plane. Now these functions describe the displacement at a given radius and an angle relative to that crack face plane. Some features that I note about this, you have continuous functions that are described that provide angular components, and you have another factor that describes radial behavior. And so I note that these are relatively easily separable. I've used that fact in other situations, and if the question comes up, I'll be more than happy to talk about it, but we're going to move on. Ultimately, what I'm looking for, note that these are infinite series, and I'm looking for these leading coefficients to these radial and angular terms. These leading coefficients ultimately describe our stress intensity factors. So these Williams expansions ultimately arise from solutions at the continuum scale to the area stress function, which really describes the stress of a material under load and geometry. And with a little bit of information such as your shear modulus and the Poisson ratio, you can convert these to displacement fields, and note that these equations actually describe the displacement of any crack, any material surrounding a crack tip at that point. Ultimately, our stress intensity factors are described by these specific three leading coefficients, which I'm going to be referring to as the Williams coefficients from here on out. So if I can obtain these A11, A12, and A21 coefficients, I can get K1 values, K2 values, and T stresses. Those are referred to as the stress intensity factors. And just so we're all on the same page, I wanted to highlight exactly what K1 stress is, K2 stress is, and T stress is, just so we all understand exactly what sort of material deformation you would see from a K1 stress, etc. So that's what these plots are. Ultimately, I just took a series of points in a box and I applied a given K1 loading. This is an opening loading, so you're pulling the material open. The original crack face plane is the dotted line here, the dashed line. So that's an opening loading. K2 is an in-plane shear where you have the top material being forced to the right-hand side and the bottom of the material being forced to the left-hand side. And T stress is a tension in the direction parallel to the crack face plane. So in the case of when we're going to be applying our model, our displacement modeling to this atomistic representation, we will actually have a combination of these and higher order terms. We can go to as higher order terms as necessary. But once again, I'm trying to find K1C, that's the fracture toughness, that's the critical stress state necessary to propagate a crack. I want to note that these Williams expansions that I talked about previously are actually, if you were to take your favorite fracture mechanics book and you were to look up, the standard approach would be to look up a given geometry and a given loading condition, and you would be able to back out, or you'd be able to just basically look up an equation that describes the stress state for a given geometry. And so the stress being sigma, the given geometry, say, being the crack depth, and the loading condition being in the vertical direction here. And so the standard approach would be to look these up. I note that this happens to be the first order solution to the Williams expansion. So we are taking these first order solutions of the stress state, or the K1 stress, and we're actually expanding it to higher order terms by modeling our displacements using the Williams expansion. Okay. So our methodology to finding those leading coefficients we refer to as a basis set projection. And it's somewhat similar to, say, a vector projection, in the sense that what we want to do is project our noisy data into that continuous space of the Williams expansion and find the leading coefficients that best describe that model. And that really rings home to a sort of a linear least squares type of approach. And in fact, this is very representative of that methodology. However, it's quite compact relative to other approaches. And so I kind of wanted to just walk through it very briefly here. We start off by defining a vector displacement function, which is ultimately a combination of our continuous Williams functions in the Euclidean directions relative to our axis here. From there, we can model our observed displacements. These are all discrete. These are all evaluated at each one of the atomic positions at a given r and theta. We can model these observed displacements in terms of these continuous functions and their leading coefficients as follows. We project the continuous Williams expansions onto the observed displacements. So this would be the inner product between the discrete observed displacements and the continuous functions evaluated at each one of the Ri and theta I observed displacements. This gives rise to a discrete vector. Ultimately, if we're looking at one M and N combination, this inner product would be the inner product of the continuous Williams functions for different MN combinations. And again, we have our leading coefficients, which we're interested in determining. And this really just boils down to a very simple linear system of equations to solve when we're considering all M and N combinations. I note that this is a very compact...
Damn it.
I'm sorry?
Oh, sorry, never mind. I didn't know I was on speakerphone.
Okay, okay. I note that this is a very compact form. The size of this matrix happens to be 2n plus 2 where n is the number of terms that you want to use in the Williams expansion. This is very small relative to a linear least squares approach, which would require an overdetermined system where the number of rows in the matrix would be consistent with the number of points that you chose within the number of atoms that you chose to model the displacement of. So it's very compact. Again, we're looking for the stress intensity factors, which are associated with these given coefficients. Okay, so we have our model, and now the idea we want to try and get at, well, what sort of error is associated with, for instance, this random noise that we will be seeing from atomistic models, and what sort of error is associated just simply with our methodology. And so what we did was we developed a toy model to explore behavior of the solution method. And once again, what we do is we take a series of points in a two-dimensional sense. We apply a known K field to it, or known stress intensity factors to it. And we use our methodology at that point to calculate what the stress intensity factors are determined as, right? And so by looking at the differences between what we know we applied and what we calculated, we can back out the error of the method. And I note that our toy model is the most ideal case in this situation. I know exactly where the crack tip is. I don't have any sort of blunting that may be consistent with the displacements that we will later see in atomistic modeling. And ultimately, I'm going to be modeling the displacement fields in an annulus that circles or that surrounds the crack tip region. And so this gives us the opportunity to explore things like, well, how about the radius? How does the radius affect the result that we see? Or how does the number of points affect the result that we see? And that's what I'm kind of showing in the following plots here. So in terms of radius of the annulus, what's interesting is obviously as you get farther and farther away, the far field displacement solution is more accurate. We find that K2 in red here and the T stress improve as you increase the radius of the toy model. However, K1 seems to remain relatively consistent in terms of error, irrespective of the radius that you actually calculate your displacement field within. Now, the middle plot here happens to be theta. Now, theta, imagine that you're just taking a points, or you're trying to model the displacement within just a small pie slice of this annulus. Now, that's kind of crazy, but maybe you have a really poor random number generator and it chooses points that are all localized into one region. What's interesting about this is the fact that the K1 stress state is very well predicted on this length scale. It's somewhat consistent over all angles. So that is to suggest that it really doesn't matter where I choose my points. If I'm interested in the K1 value, I can choose points that are localized into one small region. Similar to that, if I look at the number of points chosen within this given region, as we increase the number of points, we seem to decrease the variability in our result, but the average values are relatively consistent. And again, K1 seems to be insensitive to the number of points. What's interesting is that even at small number of points, say 10 points, the methodology can predict a reasonable K1 value on the scale that I'm showing here. And so additionally, we had looked at the N dependence, N being the number of terms that we use within the Williams expansion. And what it shows additionally, there is an increased result or a decreased percent error in K2 and the T stress with increasing N. However, what we're ultimately interested in is the K1 stress. And what our results have shown is that K1 at n equals 2 happens to be the most accurate solution for K1. So in the interest of time, I'm not showing this data. I have it at the tail end if anybody's interested. But that really dictates the size of our matrix and the size of our linear system. Again, it's 2n plus 2. So we have a size 6 by 6 matrix that we have to invert in order to solve. We use singular value decomposition to solve that linear system, just as an FYI. So continuing with the toy model, the last thing that I want to point out here is the fact that the error analysis that we were looking at previously was dictated based upon the idea that I knew what the applied field was. And I want to be able to apply the model and know what the error is, but I don't know what the applied field is. So in the case of MD, I won't know what the applied field is. So is it possible, and it is, and this is the data that I'm showing here, can we map out the space and calculate a percent error based upon what the calculated value is? So using material properties that are consistent with what I will see with molecular dynamics and parameterizing the toy model consistent with the MD model, we can span the space of calculated values for K1 and K2. And in the case where, say, I have a K2 value that I've calculated at 0.15, and say I have a K1 value that I've calculated at 0.5, I know that the percent error for K1 would be approximately 1.5, and that is simply due to a systematic error associated with our approach. That systematic error originates from the random thermal fluctuations that I've built into the toy model. It also originates from the fact that the approach is simply a least squares type of approach. But I note that this can be done for K1% error, for K2% error, and kind of a chi, which is basically just a measure of the overall accuracy of the stress intensity factors. 0 being the ideal result for each one of these figures. So this is indicative of the idea of having systematic errors within the approach, and the question is why? And I want to note that it's most likely due to the fact that we are applying linear elastic fracture mechanics in a regime that is not necessarily appropriate. We are applying finite strains to these samples relative to their sample size and relative to their crack length. And that's not necessarily in accordance to linear elastic theory, but as we'll see soon, the methodology does fairly well in predicting existing experimental fracture toughness values. So that's my next step here. Let's apply this whole methodology to our fracture samples. Now keep in mind that what I have in terms of our fracture samples, again, we're holding this type of silica configuration and uniaxial tension, and we're watching a crack propagate, right? So with molecular dynamics, the idea is that you take a snapshot in time, so you're sampling in time on a regular interval. I want to take a single snapshot. I want to locate the crack tip location. I need to locate that because the entire methodology is based upon finding the crack tip location. From the methodology that I'm using to locate the crack tip is kind of shown in this figure here. I use a methodology currently that's referred to as, we like to call it the last surviving bond technique. If you take a whole collection of points in two-dimensional space, you can kind of do what's referred to as an alpha shape. It's a convex hole, which ultimately can have a concave region as well. So you can bound a region of points with a polygon, and tracking the lowest point in that polygon, I arbitrarily dictate that to be our origin. From there, what we want to do is model the displacement field that surrounds in an annulus, and I choose R1 and R2 for our atomistic simulation on this order, and the idea was to make them as large as possible, away from the crack tip, incorporating as many points as possible without going outside the extent of the simulation cell. And so we're going to be modeling these displacement fields and ultimately determining the Williams coefficients. So at a per time step basis, I can calculate K1, K2, and T stress and see how they evolve in time. And that's what I'm showing here. So the top figure is showing the K1 stress, the middle figure is the K2 stress, and the bottom pane is the T stress. I have to note that the T stress, although it's a very interesting trace, so this is in time, and I note that the fracture sample will actually completely break in about, I think this is where it completely broke. So this is about 1.75 nanoseconds. Again, extremely fast times in the MD length scales. I note that the T stress, although very interesting, is actually 6 orders of magnitude different than the K1 and K2 stresses, and so I disregard this just simply due to the fact that it seems to be irrespective of the stress state. Note that our fracture sample, we loaded it in K1 stress, so we would anticipate that it should have a K stress that is darn close to 0, and that is indeed the case. We find that the K2 stress is very much localized about 0, and that's excellent. Note what I'm showing here, I apologize. This is 5 independent, unique fracture samples being strained at exactly 22%. And so to see that very unique configurations give rise to very consistent properties is a plus for the atomistic approach. But when we look at K1, we start off at time equals 0 at 0 stress because the displacement field does not indicate any stress, but as time propagates, we see that the crack starts to build due to the displacement of the material. Let's zoom in on just a single trace here. What you see is that the stress starts to increase. It ultimately reaches a maximum and it decreases. And this building a stress and dropping a stress is associated with propagation events, right? So the crack tip will remain localized for good durations of time. We will ultimately reach some critical stress state. At that point, we'll have a propagation event which will drop the stress, and this process is repeated. It almost seems as though for some of the samples, this initial large stress state before you have an ongoing propagating crack is almost similar to transient type behavior. So anyways, the question is, now that we have all of this data as a function of time, how do we interpret fracture toughness from this? We took 2 methodologies. Number one, we took these maximal values before propagation events actually occurred, and we averaged those across the entirety of the simulation here. The other one was we chose a very specific cutoff in time and a cutoff in distance for which, say, a propagation event occurred over, say, 5 picoseconds, and then a propagation occurred over a length scale of, say, 10 angstroms. We would incorporate that point in our averaging as well. So the 2 methodologies are looking at the maximal values and then also looking at those average values. And so we can quantify that and plot those as a function of applied strain on the material. So as we increase strain values for the material, the crack will actually propagate more readily. So the time frame that the crack remains within the fracture sample actually decreases with increasing strain. However, those maximal values and the average values seem to be somewhat consistent across this strain value. Now I note experimental fracture toughness for silica glass, pure silica glass, is about 0.8 MPa root meter. And it's nice to see that our results kind of nicely bracket this experimental result. But most importantly, the fact that the modeling result is somewhat consistent within error bars and within this kind of outlier at 0.26 strain is consistent over time is important, because fracture toughness is an intrinsic property of the material. So I shouldn't anticipate that there is any sort of strain dependence on the result. And so we're seeing somewhat consistent results. Going back to that systematic error, I can assess that now that I've calculated what my K2 values are and my K1 values are and my T-stress, I can assess that systematic error. And in all cases, it was pretty much about 2% overshooting in terms of results there. So I think that's a very nice result for an atomistic modeling where our elastic properties slightly differ from experiment, but our fracture toughness can bracket experimental results very nicely. Note that these strain values are significant. Once again, this is a feature of the fact that we're operating at nanoscale and nanosecond lengths and times. Primarily, these strain values are primarily chosen in order to have a crack propagate through the material in a reasonable amount of time, simulation time that is. These simulations can actually become quite cumbersome when it takes time to build statistics. Right? So anyways. Okay, so previously I had mentioned chemistry and how water can affect the overall bond strength of a silicon-oxygen bond. And so what we did was we added water to this system. We added water to maintain a crack tip that has a given amount of water molecules at the crack tip. And we can track, for instance, the crack depth as a function of time and compare a dry and a wet system. So these are the same two systems. One contains water and one doesn't. But what you'll find is that the dry system actually remains stuck in these energetic wells for more consistent durations of time, right? So the crack remains localized at a given fixed depth for a duration of time, whereas the wet system seems to not be quite as affected by that. And as a result, the velocity or the crack velocity, which would be the slope in this data, actually is greater for that of a wet system than it is for a dry system. But when we calculate fracture toughness of the given wet and dry systems and compare them here, note the open symbols are the dry system, the filled symbols are the wet system. Ultimately, using the two methodologies, we see something somewhat consistent with a decrease in the fracture toughness on the order of about 1%. And so it's not very significant, but it is a change in the value. And so it's interesting to observe the fact that water can play a role even at the atomistic modeling approach. And to continue on with this idea of chemistry, one of the things that I've done most recently, and I haven't yet filled in the blanks and kind of filled out this data, but I want to walk through it and kind of see if we can glean some information from it. But I've been adding different amounts of weight percents of calcium oxide to silica glass just to see what sort of effect we can interpret from this. In addition to that, I'm using 3 different cooling rates on how we create the silica. And if we look at the density as a function of increasing concentration or weight percent of calcium oxide, you see a decrease in the density. Let's see, so that's, as you change the cooling rate and you have a slower cooling rate, there's actually a densification greater than that of higher cooling rates. And that's kind of an expected result in the sense that if we slow the cooling rate down, we should find a material that is stronger, it's denser, and it's a more well-equilibrated configuration. So the idea is that high cooling rates often lock in non-equilibrium states within the glass. And by slowing that cooling rate down, we will actually densify the material. So this is kind of an expected result. We can look at some of the elastic properties, for instance, C11 and C44. C11 is related to the elastic moduli, where C44 is related to the shear modulus. If we look at fracture toughness here and note there's only 3 points, I know that 3 points don't necessarily make a trending type behavior here, but in terms of cooling rate, again, we see greater fracture toughness with increasing, with decreasing cooling rate, slower cooling rates, sorry. And then if you follow or agree with this 3-point trend, hate to say that, it suggests that there is a concentration of calcium that gives rise to the greatest fracture toughness. Okay, so it looks like I've already almost gone over my time with 10 minutes. That's kind of ridiculous there, so I'm going to jump to the end here. Just in summary, Sandia is interested in predicting aging in lifetime or reliability predictions for glasses. I think making those process structure property relationships between atomistic modeling and these continuum scale length scales is important. And I think that atomistic molecular dynamics can play a significant role there in the fact that we have chemical and structural specificity that is not typically available to other length scales. And ultimately, I hope that I've convinced you that stress intensity factors and process structure property relationships can be gleaned from atomistic molecular dynamics. So I just want to thank you. And I want to thank these people. Obviously, I don't work in a vacuum. If you know of anybody or you happen to be somebody that is interested in a postdoctoral position and you are interested in atomistic modeling, please contact me. We have an active posting and I would like to talk to you. So with that, I'd like to thank you for your time.
Thank you.
We clap. Thank you.
Thank you.
So how do you want to go about questions? Raising, just put them in the chat box? Maybe? I think what's now in the chat box is answered, or just or hand
Whoever
raising.
has a question, just unmute the where we.
Just unmute and ask. Okay.
Yeah.
Can I start?
Yeah.
So, so you have these different length scales and you talk about them, and then you gave a beautiful talk about what you do at the atomistic level. Do you have active work going on to try to bridge these length scales, in that data from one length scale I input for data in the other length scale, or work at the other length scale?
Yeah, so a lot of what we try to do, it's never a single length scale that usually tries to answer the problem. We're always trying to make connections between other length scales. And specifically, the question at that point becomes, well, what sort of information can I upscale? What sort of information is important for higher length scales? And so I've shown quite a few times, for instance, the chemical influence on elastic properties. That would be very valuable information for me to pass up to a higher length scale, at which point they would be able to parameterize their model based upon the results that I see. So that would be one approach to it. A lot of those images that I grabbed for that length scale modeling effort actually originated from a very large project where we were modeling on 6 or 7 different length scales and trying to pass information in between. So me personally, I think it's too big of a effort for me personally to try and model atomistics and phase field and kinetic Monte Carlo and finite element. We have experts that we all try to work together. So
thank you.
Yeah, sure.
Hey, Mark, this is Sachin at the top.
Yeah.
I mean, supercomputers, GPUs, what?
Oh, I missed part of the question, but I think I got the gist of it. What am I using?
Mhm.
Is that it?
Yeah, are you using a GPU cluster? Or are you using some sort of
Yeah.
32 core machines, things like that?
We kind of knocked that stuff out of the water. um, so those simulations ran for months on, oh, let's see, we were in the 400 process range. So I'm running parallel jobs, 400 processes for months on end in order to run multiple statistics, multiple configurations. Primarily, all of my work has been focused on CPU type of efforts, so distributed memory. As far as GPUs, I have been currently setting up which I'm super excited about. I'm setting up a Beowulf cluster with workstations that contain P100s in them. And so it would be a hybrid architecture that we'd be approaching. And one of the key things is in terms of using these types of hybrid architectures is whether or not the codes that you're using are written for them or can actually employ them, obviously. My bread and butter is LAMPS, which is developed at Sandia, and quite a few of the approaches and the models that I use are compatible with the GPU type base. And I'm super excited to get back at it, get back in the office, and actually start using this hybrid type computational resource that I've been working on for a while now. So, but in terms of the big clusters at Sandia, they're primarily CPU based. Yeah.
Mark, this is Sachi. I have some questions on the results you have.
Sure.
Particularly on slide 18.
18. Okay. Oh, yep.
So you are looking at a linear elastic fracture mechanics to derive your properties.
Yeah.
It assumes a sharp crack, right?
Yeah.
You clearly don't have a sharp crack.
Almost definitely.
And on top of it, you seem to have quite a bit of crack bridging going on ahead of the crack, which is more indicative of what you would see in a elastoplastic kind of behavior.
Yeah.
How do you resolve this? Because inherently there's no brittle sharp crack when you go to that length scale, looks like, from your simulations.
Oh, you're absolutely right. The blunting of a crack is a challenge, and let me jump forward, and I'm gonna share a slide here that I have. One of the issues is the fact all of the methodology is based upon correctly identifying that crack tip, and what you see here is that, you know, my typical last bridge gives rise to this location, but the low density, you know, you might find that it's actually deeper within the bulk. And it turns out that if you misidentify that crack tip, which I've done here, and I've plotted the percent error, the error significantly goes up as you misidentify that crack tip. And so what we've done is we've used a methodology. I had mentioned the separability of the Williams expansion. And what I've done is I've looked at radial displacements. Given the fact that they're separable, that means that at any radius, an angular displacement should be equivalent, and vice versa. At any angle, any radial displacement should be equivalent. And using that type of idea, what we can do is map out the space and find the ideal crack location where the Williams expansion is actually the most separable. And we identify that location as the true, quote unquote, crack tip location. From there, we apply the methodology. The presentation was getting long, and I really just didn't want to incorporate too much detail or too many specifics that I didn't think were so dramatic. But you're absolutely right. That's one of the challenges here is we're applying linear elastic fracture mechanics, which assumes a sharp crack. We don't have a sharp crack. We might be in a plastic regime. However, it seems as though we're in a regime that is radially it's K1 dominated. And so that's a good indication that linear elastic fracture mechanics approaches might be applicable at this length scale.
So once you pick your crack tip location, have you tried to track it to where you see the farthest point from there where you see separation and treat it like a process zone and see if that stays consistent as your crack moves, like an elastoplastic crack that you have
yeah,
process
that's
zone. Do you have a steady state crack growth in that case?
That is a challenge. I haven't actually done that. I guess the approach would be to some degree thresholding at that point. You know, you would be looking for a certain amount of air or looking for criterion that satisfy this plastic deformation. I haven't done that. And we are, in essence, kind of blindly applying linear elastic fracture mechanics in a regime where we know that it's very much questionable. But it seems to give very nice results for a material system that is somewhat accurately represented with atomistic modeling. So I'm kind of excited about that one.
If I may, I want to ask one last question.
Certainly.
Why was your shear modulus so off? You don't seem to even indicate it's an isotropic material, the relationship between EG and U.
It's not. You're absolutely right. The relationship between EG and U, it does not agree. And I think that's a really good question. And a lot of times when I start thinking about the air in, say, the fracture toughness, I'm relatively surprised that we have such a small air when, say, the shear modulus is off by nearly 10%, right? So to have an interatomic potential that performs as it does, but still gives rise to you know, continuum scale measures that we've gone through this whole rigmarole in order to quantify, I think is a plus for the approach. But you're absolutely right. That relationship does not hold. No, I absolutely.
It's the other way, right? The modulus is the best predicted because it's averaged, strength less so, and then fracture toughness would have the most scatter.
Yeah.
In your case, the fracture, mode 2 fracture seems to be not as bad as the shear modulus.
You're absolutely right. You're absolutely right.
I'm kind of puzzled why that would be the case.
I don't necessarily know the elastic properties really, once again, are buried in this interatomic potential, and some interatomic, you know, silica glass is actually probably one of the material systems that is most well modeled by various different interatomic potentials. And what's surprising is that even though, you know, the relationships don't necessarily hold in terms of elastic properties, surprisingly, that interatomic potential does does a lot better than some of the others out there. So yeah, I don't necessarily have a direct answer to why we see that discrepancy.
Thank you. Very nice presentation. Enjoyed it.
Thank you.
Any other questions?
Well, we're still going to have a virtual beer fest.
Oh.
Root beer booze, organic root beer booze. So the professors here are going to have to get their act together and have beers and things like that for the after Zoom meeting, stuff like that. Otherwise, I have to do FaceTime with just the real aficionados. But okay, I'm done blabbing. And by the way, Merry Christmas. You know.
So Mark,
Yeah, I have to say,
you did work on polymers as a graduate student. Now
Yes.
you're into ceramics, which is the far end of the field.
Oh yeah.
What are challenges? What are the challenges in doing molecular dynamics at atomistic simulations for polymers versus ceramics?
Yeah. I have to say that during my graduate work, what I gained is really a tool set that I've had the opportunity to apply to a multitude of material systems. And so the approach is, you know, it's one thing to build a model and to validate your model. And it's another thing to try and quantify the results that you get from your model. And I think that's probably the more interesting aspect to this, is the fact that, you know, I can go and simulate this glass because I understand how molecular dynamics operates. The next thing is, well, now I need to take that result and quantify it. And I think often across material systems, the approaches that we use to quantify these properties are somewhat consistent. You know, 2-point statistics. It's a very useful type of measure, which is applicable in both polymer and glassy materials. Identifying void space within a polymer or void space within a glass is significant and can quantify when a fracture takes place. And so I think that those types of measures are the types of things that I gathered during that Arlette taught me how to go about. And so I think that was is how I go about this in general. I think it's been very valuable, the knowledge set that I gathered from polymer systems and how I apply them to other material systems. I note that I just to let Arlette know that I haven't left the polymer world. I'm still currently working on polymer projects as well. So be on the lookout for something somewhat recently. I'm working with a Meili for Schnet right now. So
oh nice.
Yeah, so we have an ongoing project, and we hope to get some papers out very shortly here in those regards. So
send me a copy or send me a kind of an.
Yeah.
I mean,
hey, you want to review a paper?
What?
You want to review a paper?
Yeah, add me as reviewer. Yeah.
All right.
As a possible reviewer. Yeah. Thanks for your kind words. Yeah.
Yeah.
Okay, since I don't see any more questions, I want to thank Mark. It was a very enjoyable presentation, and looking forward to see you physically coming to San Diego.
Sounds good.
Yeah.
I appreciate it once again. Hey, and if anybody's out there that knows of somebody that's coming up soon, that's possibly graduating and might have interest in this type of work, obviously, please put them in contact with me. We have an open posting for a postdoctoral position that we would love to fill, and I know that there's many candidates at San Diego State that are very qualified. So thank you.
Okay.
I'm impressed that it's not frozen. All the positions here would be frozen.